Hello, my name is Sidharath and I am from IIT Roorkee. My branch is Engineering Physics and I am from third year. Today I am here for my presentation for the course Applied Instrumentation PHN 310. Now let's start our presentation. My topic is detecting light from stars. So for this topic we will go one by one, like what is light. We'll talk about electromagnetic waves, frequencies, its wavelengths and different properties and characteristics. After that we will talk about LDR, which is light dependent resistors. This is something it is of less sensitivity, a fundamental resistor which will detect light. Then after that we'll jump to very highly sensitive devices like CCDs and photon multiplier tube which will detect lights. So now let's talk about the electromagnetic wave spectrum. We can see this spectrum consists of wide range of waves like radio waves, microwaves in very high wavelength regions, and in small wavelength regions we have X-rays and gamma rays, UV rays. Also you can see that how these wave frequencies and wavelengths vary. Like very low wavelength waves have very high frequencies, and one thing you should also know that these high frequency waves corresponds to very high energies because equal to h nu, where nu is equal to frequency. So obviously this high frequency waves will have very high energy, and high energy corresponds to these high temperatures of the object which emits this type of waves. So now we have seen electromagnetic wave spectrum. Now let's discuss two of the main properties of the electromagnetic wave which we are going to utilize for detecting our light. One of the properties, as everyone knows, is like frequency is given by c by lambda and energy is given by h nu. So this is the very easy property. But this intensity, well, going too deep, the intensity is calculated using the Poynting vector over one cycle. But for now, we can say that point source emitting electromagnetic waves whose intensity can be given by power, the source power divided by area. So we are going to make use of this intensity and this energy property of electromagnetic wave to detect our light. Now, in the above image, you can see that for different temperatures, we are getting different curves with different peaks. The most important thing in this image is that at what every peak tells you is that the corresponding frequency or wavelength is what the body is emitting the most. It is the wavelength or the frequency of a wave which is getting emitted more number of times than any another wave for that body at that temperature. So now we have talked about the electromagnetic waves and its properties which we are going to utilize in detecting light. Now let's talk about the devices on which we are going to put our light and detect it. One of the most basic design device is LDR, light dependent resistor. We will talk about why it is called light dependent resistor after this slide. First of all, let's talk about its construction. Its construction is very easy. It has two metal contacts and it is separated by a snake-like track which is made up of cadmium sulfide. And this snake-like track gives you the maximum contact area with the metal contacts. So this is the basic constructions, and now we'll talk about its working. So now let's discuss its working. When the light of sufficient energy falls on the semiconductor, like cadmium sulfide, which our LDR is made up of, then these holes or electrons gains energies from the photons of the light and it jumps to the conduction band where it acts as a free charge and contributes toward the conduction, and that's why its resistance decreases. One should also take care that the light which is falling should be greater than a particular threshold energy, and that threshold energy is this energy gap between the conduction and valence band. At least that much energy has to be provided to the electron to jump from the valence band to the conduction band where it can contribute toward the conduction. Also, when the light energy is greater equal to threshold energy, to increase the conduction, we can also vary it with the intensity of the light. As the light intensity increases, the number of electrons interacting with the photons increases, and due to this, there will be more number of jumps from the valence band to the conduction band, and hence more number of free electrons available for the conduction, and therefore resistance decreases. Now, one should ask, like, how we can change the threshold energy of our semiconductor. Well, we can do that with the help of doping. What we are using before was intrinsic semiconductor, and in that what happens, the Fermi level is between the conduction and valence band. Hence, what we can do is we can dope our semiconductor with n-type or p-type, and because of that what happens, the Fermi energy level goes closer to the conduction band, and the energy needed for electron to get transferred to the conduction band is now less. Hence, the threshold energy required for this type of semiconductor is less. And hence we can vary our hence we can say that we can vary our threshold energy by doping. Now let's discuss the characteristics of LDR, like what will happen when the intensity of and the energy of light varies. So here in this graph you can see how the resistance of the semiconductor or LDR varies with the intensity. At this position, the intensity is very low. That means the electrons interacting with the photons are low, and hence a very less number of electrons are jumping to the conduction band, and hence the resistance is very high. When the intensity increases, the interaction with the photon increases, then more number of jumps of electrons happens in the conduction band, and hence the conduction increases, therefore resistance decreases. Well, we can also see some more characteristics like LDRs are very sensitive to changes of light, and also one of the most important things, the range of light within which resistance varies is specific for a particular LDR, and beyond this range the response may become non-linear or saturated. Now, as we have discussed about LDR, the disadvantage of LDR is that it is very low sensitive. It needs a good amount of intensity of the light or energy, like threshold energy, to detect it. So now let's move to some another devices that is more useful in detecting light, more high sensitive, and detect faint lights, as the light coming from stars are very faint, and these devices are very useful in detecting lights and telling about properties like wavelengths and frequencies of it. So CCDs are charge coupled devices, and it is used for capturing images in various applications, as you can see here, and it is employed in telescope from to detect and record light from celestial objects. Now let's discuss about its working and its properties. Now let's discuss about the working of CCDs. First, like we can compare it with like putting thousands of LDRs in one place, and hence we will increase the sensitivity. But still, it will be a little bit expensive. It will occupy more space, and it will consist of too much noise. So what we are going to do is we are going to use CCDs in that place. In that, what we do is in a place we put thousands of pixels. Pixels are very few size, so putting thousands of pixels in one place will be not that much costly. And that pixels are light sensitive, and because of that, when light falls on those pixels, photons are generated. When the photons fall on these pixels, the electric charges are generated. This charge is then transferred from devices pixel by pixel to readout register. And this readout registers when the electron or electron charge is detected, we get to know about the properties of the light. Well, this is what I told you in the previous slide, what type of sensors are used in the CCDs and how they operate. These sensors are small pixels, and the small pixels interact with light, generate electron charge. Those electron charge on applying voltage passes from one pixel to another pixel, and it transfers to the readout register, where we get information about the properties and the information about the light, like what type of wavelengths and frequencies it consists of. Now coming to the advantage of the CCDs, they are very highly sensitive. What highly sensitive means is that they are very high quantum. They have very high quantum efficiency. Like this means that they are very efficient in converting the incident photon to the electron charge. And coming to the second advantage, that it has a very spatial resolution, and also it can detect light in a very wide range, from ultraviolet range to nearly infrared. Now, let's discuss another device which is used for detecting light, which is photomultiplier tubes. It's a highly sensitive device to detect light, more sensitive than CCDs. It can even detect a single photon. What happened in this? When an incoming photon falls on this photocathode, well, this is a vacuum chamber in which everything is there, like anode, diodes, and the photocathode window. So what happened? The incoming light or photon is made to fall on this photocathode. When this photon fall on this, the electrons are generated due to the photoelectric effect, and then it gets reflected, passed to the diodes, and from one diode to another diode, and every step, due to the photoelectric effect, more number of photon or electron is generated, and it is passed one by one, and hence the intensity increases. So we can say we fall a very faint light on the photocathode, and in return we get a very dense intensity of light, and now we can use this light to detect the properties and everything, wavelength, frequency, etc. This is the working, which I explained you in the previous slide. You can have a read on this, like how there are a series of diodes and anodes contained in the vacuum tube, and how these electrons are accelerated toward the first diode, and then from one diode to another diode. So you can have a read on this. Now let's discuss the sensors and operations of the PMTS. The sensors used in PMTS are the photocathode, which is made up of cesium and gallium arsenide, which emit electrons. Now the operations is, again, this is the same. The electrons which is emitted by the photocathode is passed from one diode to another, and when during this process the electron imparts each diode, they causes the emission of additional electrons through the secondary emission, and hence due to this the intensity of the faint light increases, and which is then detected at the anode. Now coming to the advantage part of our PMTS, the two main important advantages of it are that it is very highly sensitive, so much sensitive that it can detect individual photons, And the second advantage is that it has very excellent signal to noise ratio, which are particularly useful for detecting faint light signals like that of stars, which we are going to explore in astronomy. Now coming to the marketing purpose, well, it can be used in wide areas like in uh, high physics lab where particle is involved, or lab where very high sensitivity for the light is to be cared. Also, it can be used in armies, and yeah, the main thing where it is useful is detecting light from stars. We can have many things, many informations about the stars from this. So we can have a training and education for these type of instruments, and hence it can be used in various regions for good purpose. So here my presentation ends for my topic, detecting lights from stars for the course PHN 3 and B at night instrumentation. Thank you.